Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Today, inshallah, is the third lecture of the prediction session. Inshallah, we will talk about the least squares method. Let's first review what we have studied last time. What we covered last time is linear regression. So what is linear regression? The goal of linear regression is to predict the value of a variable given the value of another variable. So here we predict y using x. And one way to do that is to find the regression estimate or the regression line of y given x. How to do that? First, we need to convert the given value of x to standard units. Once we do that, we multiply by the correlation coefficient. And when we multiply the given value of x by r, then we get the estimated value of y. But there is a problem with that, which is that y now is in standard units. So it's not in the original unit of the variable y, but the estimated value of y now is in standard units. So we cannot actually do exactly these steps. We cannot just convert x to standard units, multiply by r, and then get the value of y, because y will be in standard units, but we need it in the original unit of the y variable. So we have to convert it back to the original units of y, and to do that we have to go back to the original units. So if we look at the standard units space, we'll find that y will be r multiplied by x. So this line has a slope r and it goes through the origin, so the intercept of it is 0. So the linear equation of this line is y equals r times x. That's why if we converted x to standard units and multiply it by r, then we can get the estimate of y, but this will be in standard units. To do that in the original units, we have to find out the slope in the original space. The slope in the original space, as we saw last time, will be r times the standard deviation of y divided by the standard deviation of x. And generally, this line will not go through the origin. It might be, but it's not always the case. So the intercept of this line, as we saw last time, will be the average of y minus the slope times the average of x. Here is the summary of what we got last time. The slope of the regression line is r times the standard deviation of y divided by the standard deviation of x. And the intercept of the regression line, which is the part of y, or the value of y when x is 0, will be the average of y minus the slope times the average of x. And eventually, the estimate of y given the value of x will be the slope value times x plus the intercept. So that's the predicted value of y given x. And that's the equation of the linear regression line. We saw that on an example, if you remember, the relationship between the height of the parents and the height of the child. And we tried that in two different ways. The first one using the nearest neighbor prediction, which is the idea that we tried earlier in the course, which is indicated here by the gold points, and the regression line, which is indicated by the blue points. And we saw that the regression line is very, very close to the nearest neighbor predictions, which means that the regression line captures very similar idea, which is given the value of x, y, the estimated value of y on the regression line will be the average of the values of y in the original dataset. So that's what we covered so far in the session, and in particular the last lecture. Today, inshallah, we will cover the method of the least squares, or the least squares method. And in this lecture, we will be concerned with whether the regression line that we estimated last time, or that we studied last time, is the best line we could find for the relationship between the two variables or not. That, of course, is related to how good the line is fitting the dataset that we have. So we have to think about this in terms of an error. So whenever we have an estimation or prediction, there must be an error. So the estimation might not be perfect. So the error generally is the difference between the actual value and the estimated value. Okay, so if you look at the example here, so every point here, let's say that we took a value of x here, all of these points are not on the line. If we look vertically here, all the dark points here, here, and here are not exactly on the line, which means that the predicted value that is exactly here is different from those points. So for every one of these points, there is an error, which is the difference between the actual value, let's say that this value, and the predicted value, which is here. Sometimes, of course, this difference can be positive, so the actual value minus the estimated is positive, or might be negative, like in this case, if we took this point, then this value minus this value is negative. So the error can be positive, or sometimes it can be negative. So if we just say that the quality of the line, or how good it fits the data set, is captured by the sum of errors, of course some of the errors will cancel out the others, because some are positives and some are negatives. So to deal with that, we either, as we discussed earlier in the course, we either convert the values to absolute values, so we can talk about absolute errors, or we can also take the squares of the errors. And that's what we did in standard units, and this is what we will do also in this lecture. So to measure the rough size of the errors, we will square the errors to eliminate the cancellation. Remember, the goal of this is to see whether the regression line is good enough to represent the relationship between the two variables or not. And to quantify how good it is, or the quality of the line, we need to compute the error between the estimated values on the line and the actual values in the data. So what we will be doing here is to try to estimate the error in a systematic way. So to do that, for every given value of x, we will compute the estimated value of y, and we will compute the error for that given value. We will square all of these errors. Then we take the mean of them, so that will be the mean of the squared errors. Then we will take the square root of that mean, so that we get back to the original unit of y. So up to this step, when we get the squares of the errors, so the unit here is the square of the unit of y. If we take the mean, still the unit is the square unit of y, but now when we take the square root, we will get back to the unit of y. So this value of error is called the root mean square error. So we'll compute the error for every given value of x. We square the error so that we can eliminate the sign. We get the mean of all of these squares, and then we get the square root of that mean. Root mean square error. Now let's see a demo on how to do that. We will start with defining a function that will get a table and the two variables in that table, of course two columns, and it will compute the slope and the intercept of the regression line given the functions that we saw last time, and then compute the predicted value for each value of x. So the predicted value of y for each value of x using the slope and the intercept. So this is the equation of the regression line. It will compute that for every value of x, and it will return an array of the regression's estimates at all values of x. So we'll use that inshallah later. Now the data set that we will work on is called the district demographics data set. In this data set, we have one row for each district or area in a state in the United States. For each district, we will have the median income for the population of that district or area, the percentage of them who voted for Clinton at that time in 2016 presidency elections, and this is the percentage of the population that went to college. So this is an indication of the level of education of the people living in that district. And we have here, as we said, one row for each district. So we have like 430, maybe 5 rows here. So let's focus only on two of the variables here, the median income in dollars and the percentage of the population who went to college. And let's plot the relationship between these two using the scatter plot. So here is the percentage of college, and here is the median income. And as you see here, there is of course linear relationship, kind of correlation between the two variables. Let's compute that correlation using the function that we defined earlier in the session, in the previous lectures. So we got 0.8, which is kind of a strong relationship, strong linear relationship, because we are talking again about correlation. Now let's compute the regression line. So to compute the regression line, we need to compute the slope and the intercept of the regression line using the functions that we defined last time. So if we do that, we'll find that the slope is 1,270 and the intercept is 20,802. Now let's compute the predicted values, the predicted or estimated values of y given all values of x using the function that we defined earlier here, the fitted values function. So we will pass to it the demographics table and the two columns that we want to compute the regression between them, the college percentage and the median income. And once we get the values back, the predicted values, we will add it as a column in the table. So we'll do that, and then now we will plot the values of the college percentage on the x-axis and the other columns on the y-axis, which are the median income and also the predicted values. So now we will see both. We'll see the actual values, which are those that were here, and also the estimated values, which are all located on the regression line. So that's now the regression line, the gold points. And now we can compute the error of that line, or the root mean square error for that line. How can we do that? The first thing is to compute the errors between the actual values. The actual values is of course coming from the median income column. That's the actual values of the income, and the predicted are the predicted income given the level of the education, represented by the percentage of people who go to the college. So the errors will be actual minus predicted, and now we add it as a column to the demographics table. So now we will see the median income, the college percentage, the linear prediction, which is predicted using the fitted values function, and the error that we just computed, which is the difference between the median income and the predicted value of the income, which is here the linear predicted value. So as you see here, some of them are negative, some of them are positives. Actually, there's only one positive here, and many of them are negatives, which means that probably in the very first number of rows here, these values are under the line, and that's why we are seeing the negative values here. Okay, because we subtract the actual values minus the predicted values. Now, to compute the root mean square error, remember, we get the errors, we square them, we get the mean of the squares, and then we get the square root. So we'll have to square the errors, then get the mean, then compute the square root of the mean, and that will give us the root mean square error for that line, which is 9,398, as you will see here. We have defined the function which is called demographics errors earlier in the notebook here, and that function will plot for us the regression line using the slope and the intercept, and also will show us some of the errors of some of the points. So you can look at it, but let's use it here and see the some examples of the errors. So the blue line here is the predicted regression line, okay, and the vertical red lines here indicate the error. So that's the error for that actual value. So that's the difference. The length of that vertical line is actually the absolute value of the error. In that case, of course, the actual error is negative because this value is less than the predicted value. So this is negative, this is positive, this is negative, this is positive, and all of them are errors. So what we actually do when we compute the root mean square error is for every point here, you see these gray points. For every point in these gray points, we compute the error. Okay, we compute the square of each error. We get the mean of all of these squares, and we get the square root of them, and that will be just one number that will quantify the error when we use this regression line between these two variables. Now we would use this function, the output of this function, along with the value of the root mean square error. So we'll not just compute, we'll not just plot the regression line and the data, but we will also show the root mean square value. So this is the prediction, and this is the mean square error, the error, squaring it, getting the mean, and finally getting the square root of it, and we will print it along with the plot. So that's the function. Let's use it with the regression slope and the regression intercept that we got earlier. So where's the regression slope and regression intercept? These are the values that we got earlier. Okay, so we will use them to plot the regression line along with the errors and along with the root mean square error. So that's the same plot, but additionally we got the root mean square error. Now back to the original question from which we started all of this, which is whether the regression line is the best line that we can get to represent the relationship, the linear relationship between the two variables or not. Now, in order to say that it is the best, it should logically be the one that has the minimum root mean square error. So the one that will give me the minimum error between the predicted values and the actual values should be the best. So let's try other lines than the regression line and see what will be the root mean square error for them. So we'll try one line here with a slope of 1,500 and an intercept of 20,000. Let's use the same function. Here is that line. Of course, it is different, a bit different. Maybe the slope is a bit higher than the slope of this, which is the case here. If you remember, the value of the slope here was 1,270. The slope that we just plotted is 1,500. Okay, this is the slope, and this is now the line, the new line. And you will see, of course, that the errors will be different. Okay, when we change the line a bit, the orientation of the line, of course, the errors will be different. So the root mean square error in this case is about 11,600. Here we had 9,000 only. So still the regression line is better. Now let's try a different line with a negative slope. So with negative slope, with also some of the errors here plotted, you will see that the errors, of course, will be higher. Okay, because originally the data has a positive correlation, but the slope of that line here is negative, so we expect that the error will be much higher, which is the case. The error here is 30,000. The root mean square error is 30,000 and something, which is much higher than this one, which is also much higher than this one. Okay, so these are three examples, and the theory says that the regression line is actually the best line, which means that it minimizes the root mean square error with the original data. So the regression line actually is the best. So the answer to the question is yes, the regression line is the best. The proof of that is out of the scope of the course, but you need just to know that with the least squares method, we get the regression line that we established last time to be the best possible line that can fit the data, which means that it has the minimum value of root mean square error. So let's get back to the slides. So this line also is called least squares line. So the least squares line minimizes the root mean square error among all possible lines. So of course we saw here two other examples, but if you tried all the possible lines, of course we have infinite, but if you tried them all, if it happened that you tried many of them, you will always find that the regression line that we established already is the best among them, which means that it minimizes, it has the minimum error among all of them. So eventually, when we try to minimize the root mean square error, we also minimize the mean square error, because the square root here doesn't make any difference on the best values. So whatever line will minimize the mean square error is also the same line that minimizes the root mean square error. So minimizing both will give us the same thing. The least squares line is called also the best fit line, the least square line, or the regression line. All of these are names of the same thing. So whenever you hear regression line, it's the same like the least squares line, and it is also called the best fit line. So traditionally, when you want to get a minimum value of a curve or a function of an error, we use what we call numerical optimization. So numerical optimization is an approximation way to minimize a given function. Although it is approximate, but in many cases it is very effective, which means that it is very close to the actual minimum of the function. And that's why so many machine learning algorithms use numerical optimization or numerical minimization to find out the best model that fits a given data set. Now, to formalize this, let's say that we have a function called mean square error, and that function takes the slope and the intercept of a given line. So we want to compute the mean square error of that line, given, of course, a given data. So this function returns the mean square error of the estimation using the line that is estimated by a times x plus b. So a is the slope and b is the intercept. Then we can use a very nice function in Python called minimize. This function takes the function that we want to minimize, and it will return the values of the parameters of this function that will get the minimum value of that function. So again, we have a function, and that function has parameters, let's say a and b, and we want to get the values of a and b that will give us back the minimum value of the function. That's exactly what the minimize function is doing. So it takes this function that we want to minimize and returns back an array of values, one for each parameter. So in this case, if we give it MSE or mean square error, it will give us a value of a because we have a here and the value of b because we have b here. Okay, so it will give us back two values, and these two values give us the minimum value of that function. So in our case, a0 is the slope and b0 is the intercept of the line that minimizes the mean square error among all lines with arbitrary slope and intercept. That means that among all lines. So among all possible values of a and b, a0 and b0, which will be returned by this minimize function, will give us the minimum value of that function. Let's see that in practice. So let's apply that on a general function first. Let's say that I have a function y equals x minus 2 squared plus 3. And I want to minimize that function. I want to get the value of x that will give us the minimum value of y. Let's plot that function. We'll see this is a quadratic function, of course, and we will see that the value of x that will give us the minimum value of y is 2. Okay, so the minimum value of that function is this value, and the value of x that gives us that minimum value is 2. So what we will do in order to use the minimize function, that we define this function as a Python function, f of x. So f of x returns here x minus 2 squared plus 3. So we'll define that function and we'll pass it to minimize. Now, when we pass it to minimize, minimize will find the value of the parameters of that function that will give me the minimum value of that function. So how many parameters this function has? Let's look at the definition. It has only one parameter, which means that the minimize function will return back to me just one value. Okay, and this value should be 2 if that function will give me the actual best value or the actual value that will minimize that function. Let's see what will happen. it gave me 1.99999, which is very, very close to the actual value of 2. Okay, here's another example or another function that's more complicated function. We'll put it in a table so that we plot it. So this function is 2 sine pi x plus x cubed plus x to the power 4. So it's really complicated and it's not very easy to find the minimum value for it. Let's plot it. And when we plot it, we see that, of course, visually it is easy to say that the minimum value of that function will happen here, which means that x will be minus 0.5 to get the minimum value of the function, which is minus 2. Okay, so this is a more complex function, of course, than this. Let's define the function, okay, in a separate Python function, and then call the minimize for it. Now, what are the parameters of that function? Again, it is just x. So we expect the function to return back one value, which is minus 0.512, which is, it's not exactly, of course, minus 0.5, but it is close enough to it. Okay, so you saw that the minimize function will not always give us the exact value, because as we saw in the slide, this is an approximation. Okay, so numerical optimization is always an approximation. So the approximation of the minimum value is minus 0.1264 and so on. So which is, of course, as you see, not very far from the actual value. Now let's minimize the root mean square error. So we'll first define a function that that will compute the root mean square error so that we can minimize it. Because it will work on linear equations, it will be defined by two parameters, the slope and the intercept. And for that, of course, we will be assuming that we are still working with the demographics dataset. So we know the columns of the two variables. We'll do the estimation, we'll compute the estimation, and we'll compute back the root mean square error. So this function will return back the root mean square error. Now let's see the root mean square error for the two lines that we saw earlier, other than the regression line. So this is the first line other than the regression, the 11,001, and this is the 30,001. Now let's pass this function to the minimize function and see what we will get back. Now what should we expect? How many values we should expect out of this function? It depends on the number of parameters of this function. The parameters of this function, of course, are 2, the slope and the intercept. So minimize of demographics root mean square error will return back an array of 2 values. This is the slope and this is the intercept. Now, how far is that from the regression line? So that's the minimum values, that's the line that minimize function thinks that it is the best for the root mean square error. The one that minimizes the root mean square error. How different is that from the regression line? Remember, we had the regression slope and the regression intercept from the early computations. Now, how different is that from the regression line that we saw earlier? So remember, we had the regression slope and the regression intercept from previous computations. Let's print them again and compare. So these are the values, the slope and the intercept from the minimize function, and these are the slope and the intercept from the regression equation that we used earlier. You will see that they are very similar. They are not exactly the same, but they are very similar to each other, which means that the regression line again is the best line, which means that it is the one that minimizes the root mean square error. Now we will switch to another example, which is nonlinear regression. So in nonlinear regression, sometimes we find that the relationship is not linear, and we want to see another type of relationship which might be nonlinear. So let's do that on a new dataset, which is called ShotPot. So this is a dataset about athletes. For each athlete, we have the weight that this athlete can lift. So this is weight lifted, and the distance that the ShotPot can be thrown by this athlete. So let's compute, or let's plot the relationship between these two variables. We will see that it is also kind of linear here, but the initial value is not maybe fitting a line. So let's first fit a line. So we will define a new function specific for this data set, and we compute the line using the so let's compute the root mean square error for any line for this data set. So the function takes the slope and the intercept and do the estimation and compute the root mean square error for that line. And let's try to minimize this function to get the best line possible, which is the regression line that as we know now. So here is the regression line that we got for that. Now let's compute the root mean square error for it. So that's the root mean square error, which is 1.219. So that's the regression line for this data, and that's the root mean square error. Now let's plot the regression line along with the data set and see how it fits the data. So as we said, it is kind of good here, capture the average values here, but it's not as good here, and of course it's not as good here. So let's try another type of functions, which is the quadratic function. So in the quadratic function, we have, of course, three parameters, a, b, and c. So the function is ax squared plus bx plus c. So now we want to get the best quadratic function that can fit this data, which means that we want to get the best function, which means that we want to get the function with the minimum root mean square error. To do that, we will use the minimize function. And to use the minimize function, we have to define the root mean square error for this data set for this kind of functions. So this function has three parameters, a, b, and c. We will compute the estimation, which is ax squared plus bx plus c. We will compute the root mean square error using the same, of course, way we did it before. So that's the function that we want to minimize. Minimizing this function means that we need to find the values of a, b, and c that will give me the minimum value of that function, which will indicate the equation for the quadratic function. So let's minimize it. When we minimize it, of course, we'll get three values this time because the function has three parameters, a, b, and c. Now let's do the prediction, okay, using these parameters. So the prediction will be, of course, this is x, so x squared times the first value plus x times the second value plus the third value. Okay, now we'll add that as a column to the table and plot it. Okay, and plot it. So now the gold points here are coming from the quadratic function, which is the best among all the possible quadratic functions, which means that it is the one that minimizes the root mean square error. Now you see that it is good here, it is also kind of good here, very good here, and bit better than the linear function here. So we want to see whether this is actually better than the linear function or the linear regression. How can we do that? Of course, we should compare the root mean square error for both. So here is the root mean square error for that function. It is 0.981. Okay, so remember that number, 0.981. What was the root mean square error for the regression line? Let's get back here. You will find that it was 1.219. So 1.219 for the line and 0.981 for the quadratic curve, which means that the quadratic function is a better fit than the line. With that, we end this lecture. Inshallah, we'll talk to you in the next lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.